Okay, so we've got a maximization problem. You know how she goes, okay? I'm gonna write it down and then we're gonna solve it. Okay, so right here we have our maximization problem where we're maximizing for x1 and x2. Should make that more clear. And then we have our two constraints. So it's subject to this and that. And so you know what we're going to do? We're going to set up our Lagrangeans, whatever you might call it, and then we're going to perform two first order conditions with respect to x1 and x2. And then I believe we're solving a series of equations at some point. And this question is all about trial and error. And so I'm going to show you one instance where we are solving assuming one thing and it turns out to be wrong. And then I kind of give you my train of thought about how I got to the right answer or how we could get to the right answer. There's also another way where we could have went wrong, but I'm not going to go over that because I feel like me showing you how to get from wrong to right once is more than enough. You really don't need any more examples, in my opinion. I'm going to set up the Lagrangian now, and then I'm going to perform the two partial derivatives, and then I'm going to explain from there on what we're going to do. Okay, so I'll show you what I've done here. So this is your Lagrangian. It's a little bit long, but it's quite simple. We're putting the maximization first, so copy and paste, and then with the two Lagrangian multipliers, we're putting the constraints or the subject to's in brackets here, and obviously it's less Lagrangian 1, the constraint, less Lagrangian 2, the constraint. And then we're performing our two partial derivatives with respect to x1 and x2 after that. So this is all like sort of like the fundamental like first steps. They are always that you're always having to do. And then I'm going to write the complementary slackness conditions, which you could have written at any point because I mean, part of it is already right here, so I won't rewrite this. But obviously, you've got this to be true and that to be true. And then also, this all has to equal 0. I don't even know if I should probably write it, but it's not like a surprise to anyone. Might just take up a lot of the board here, but like whatever. There. So that's a 0. That's not a very good 0. Okay, so this right here and then that right there, those are our constraints. We've set up our partial derivatives, and now here comes the trial and error. So we want to find out where we're maximizing, right? And it's all going to depend on sort of where we set, because we don't have an explicit answer yet, so we need to set things up. So the first thing I'm going to write assume our Lagrangian 1 and Lagrangian 2 greater than 0, okay? They can be greater than 0 or equal to 0, okay? So we're just assuming that they're both greater than 0. That means that what's in the brackets has to equal 0. So therefore, our x1 plus 2x2 has to equal 2, right? Because that needs to fall to 0. And less x1 plus x to the power of 2, has to equal 1. Okay? So these two things have to be true. Correct? Correct. All right. I'm not going to do any sort of math for this, because this should be very, very obvious. We have a unique solution at x1 equals 0 and x2 equals 1. Okay? You could take longer trying to solve this, but there's really no point. I mean, yes, you should make sure that this is a unique solution. However, in this case, these are so easy. You could look at it, put x1 to 0, and then see that x2 obviously has to equal 1. And there's no other way of really coming up with this solution. Okay? Like, there's no other way. You should be more certain about it. Like, you shouldn't just look at it and then just know. Like, you should do some math with it, but I'm not going to bother because we're going to be doing a lot more math later. Okay? So now we're going to insert these points back into the FOCs, and then we're going to solve for the Lagrangians. Okay? So for dx1L, it is going to fall to 6 plus 2 less Lagrangian 1 plus Lagrangian 2 equals 0. Okay, and so what we're going to do here is we're going to put, we're going to make Lagrangian 1 less Lagrangian 2 equal 8. Okay, and this is going to be important for later because now we're solving a series of equations. And then for the next one, you've got less 4 that now we're solving for dx2L. Less 4 less 2 Lagrangian 1 less 2 Lagrangian 2 equals 0. Also, there's different ways of doing this. This is just how I did it. Okay? And so this is going to lead to Lagrangian 1 plus Lagrangian 2 equaling less 2. At this point, this is a huge red flag. This is a massive red flag, because if we're assuming that our Lagrangian 1 and 2 are greater than 0, then two things that are greater than 0 cannot equal something that's less than 0. This is less 2, so we already know something's up. But we're going to finish this, okay? So if we know this equals 8 and this equals less 2, then we're going to put these two things, we're going to add them together, okay? So Lagrangian 1 less Lagrangian 2 plus Lagrangian 1 plus Lagrangian 2 equals 8 plus less 2, okay? Yep. And we're gonna get to this, okay? We're just gonna finish this off. So this is gonna get rid of our Lagrangian 2. You're gonna be left with this equals 6. And so Lagrangian 1 is gonna equal 3, okay? Well, if this equals 3, we know that this equals 8. We can do 3 less Lagrangian 2 equals 8. So we can move that on the other side. We can move that. So, sorry, this is a 2. So Lagrangian 2 is equal to less 5. This is wrong. This is not possible. It needs to be greater or equal than 0. And right now it's at less 5. So since our second Lagrangian is less than 5, we know that this assumption is wrong. So this is what my thinking process was. Because it's trial and error. Like, we need to find out where we're maximizing here. We need to find an optimal solution, okay? And so if our second Lagrangian is below 0, which it can't be, which it's not allowed to be, I'm just going to move this up to 0. Because then I think we'll be able to find... It doesn't make any sense to me to move our first multiplier to 0, because it's already above 0. It's good. This isn't like a great strategy, and it can go wrong. That's why it's important to really, really make sure you've got the right answer. But for our case, a little bit of a spoiler, we get the right answer now after we set our second Lagrangian to 0. But you should set the first one to 0. Make sure that it's actually correct what you're doing, or it's the most correct solution, because you don't want to get caught sort of like not looking for the correct solution to completion. And that just like you just need to make sure everything's checked. I'm not checking everything here. Like I'm not checking to see what happens when our first Lagrangian is at 0. So we're going to change the assumption here. And then we're going to solve this new problem. 0. Okay? Or we're assuming so. I guess I should have wrote that, but I don't really care. Okay. So oh brother. Okay. We're gonna get by this quick. I don't want to bother. I don't even think it's very important. So we know x1 is equal to 2 less 2x2. Okay? So we're just gonna we're gonna plug this in somewhere else. We're gonna plug this in. Which one are we plugging this in? This. I'm out of my mind. Okay, yeah, we're we're plugging into this. Sorry, guys. I'm whatever. Just trust in the process. Okay, so we're gonna be. So I've reoriented this. I've kind of messed with things a little bit, but it's all gonna make sense. Okay, because we're gonna replace our x1 our x1 with this. Oh my god. Stay with me here, guys. I'm sorry. This isn't complicated at all. I'm skipping a few steps that I took when I solved it. So I'm just tweaking just a little bit. Okay. So now we have this. This is not a hard solve. We got 4 bracket 2 less 2x2 bracket less 2x2 less Lagrangian 1 equals 6. And so we solve for our first Lagrangian, and we know it equals 10 x2 less 2. And then we can kind of also, we're putting this exact same thing into this problem. And before we did this, you didn't see me because I didn't actually do it on here, but I divided everything by 2 because it's just a lot easier to work with. Okay? And so imagine this is coming down here. We solve for it again because we know that this is the case. Okay? And this is going to give us 2 less 4x2. Okay? So bada bing, bada boom. And we put them equals to each other because we know that's going to be true because Lagrangian equals Lagrangian. Come on now, guys. The same thing. 2 less 4x2. So right. Okay. And we find out that x2 equals 2 over 7. Just trust me, okay? Because you're just solving this. This is easy math. I'm not going through the steps. And then you plug it back in. You find that x1, because remember, we have this formula for x1. x1 is equal to 10 over 7. So far, everything is good. These are positive, okay? They kind of sort of need to be positive. There's certain constraints that would lead someone to believe that they'd have to be positive. I'm going to just say that, but we'll just see. But so far, this looks pretty good. Like you don't like to see negatives here. Like you're not making a negative amount of something in an economics problem. Okay, don't do that. Don't sell someone negative stuff. And then you're plugging it back in, and you find out that your Lagrangian 1 is equal to 6 over 7. Okay, which is perfect, and your Lagrangian 2 equals 0. So everything is good now, right? Everything is satisfied. This is satisfied. This is satisfied. And we can make sure these things are satisfied as well. We already know 1 is, and we can test for this one as well. I guess we're being testing for this one. Nope, we do test for this one. Again, I am tweaking. This is this turns out, if we plug in our numbers, this turns out to be less 66 over 49, which is definitely less or equal than 0. So our answer is complete and satisfied at these coordinates right here, or at those. We have properly maximized, and we have found our solve, and everything is satisfied. We have just tested out the last component to make sure that it is satisfied, and it is. So we're all good. Deep breath, guys. We solved it again. If you wanted to be super prudent and you wanted to make sure that you were checking everything, you'd set your first Lagrangian to 0 and you'd see what that would give. It does not give you what you want. You do not want to be doing that. And so this answer is complete, and wasn't that difficult. It's just sometimes can be quite a bit of writing.